So this will be our first video of chapter 8. We're still in the larger unit on bonding. Last chapter, we went into great detail about ionic bonding and metallic bonding. And in chapter 8, we're going to be looking at covalent bonding. And we already know something about covalent bonding because we had to learn a little bit about it when we were comparing it and contrasting it to ionic bonding. And if you look at this graphic over here, you can see that there's a few examples of molecules that exhibit covalent bonding. But let's start by just going through the overall, definition of covalent bonding from that we probably had studied in years past. So looking down here, covalent bonding occurs when atoms, and this is the big thing, they share pairs of electrons instead of giving and receiving, because giving and receiving, that's what ionic bonding is, right? The pair of electrons that's shared is included in the outer shell of both atoms. These electrons that are shared are the valence electrons. We've talked about how valence electrons are the ones that are involved in bonding. And we know this covalent occurs only between atoms or two atoms that are non-metals. And so if you look at these examples, notice that when I drew in the electrons, I used different colors. So in nitrogen is often symbolized in blue. And this is because nitrogen is the major component of the atmosphere and our sky is blue. So you can see nitrogen, we know, has 5 valence electrons. And so you can see in this first ring here, I'll just highlight this first ring. This first ring, that's the 1s orbital. And then the second ring is the second energy level. And we haven't designated s and p orbitals, but we know that nitrogen has 5 valence electrons. And so you see going around that nitrogen, you see 5 blue dots. Well, nitrogen, like every atom, it is most stable when it has a full outermost energy level. And that is including 8 valence electrons. So therefore, it has 5, which means it has room for 3 more valence electrons. How does it get those 3 more valence electrons? Well, unlike in ionic bonding, it shares its electron with, in this case, 3 hydrogen atoms. So you can see hydrogen has 1 valence electron. It's represented here in gray. And in each of these bonds are composed of the sharing of 2 electrons. We have hydrogen sharing its 1 valence electron, nitrogen sharing 1 of its valence electrons, so that each atom seems to, gain another electron through sharing. You can see the same thing happens with oxygen. This is, of course, water, right? Oxygen has 6 valence electrons. And sometimes these electrons are in what we call lone pairs. Those are electrons that are valence electrons, but they're not involved in bonding. That's why we call them lone pairs. And then we have bonding pairs. Those are the electrons that are involved in bonding. And we can see the same thing happening here, where oxygen shares 1 of its valence electrons with hydrogen. Hydrogen shares its 1 valence electron. And if we look at the completed molecule, the outermost energy level of oxygen, right, this outermost energy level, now contains 8 electrons, which means it has that noble gas electron configuration, which is very stable. And we can see the same thing actually happens for hydrogen, right? Hydrogen only needs 2 valence electrons to have a full outermost energy level because it would have the same electron configuration as helium. Over on the left in blue, I talk about how molecules get their shape. And that's one of the things that we're going to talk about an awful lot in this chapter are the shapes of molecules. And how the shapes of molecules form is the idea of these lone pairs and these bonding pairs of electrons repelling each other in 3 dimensions. We know electrons are negative, we know like charges repel, so those bonds in lone pairs are going to try and get as far away from each other as possible. That's going to give us really interesting shapes like tetrahedral, bent, trigonal pyramidal, seesaw, T-shaped, square, square planar, square, pyramidal, all sorts of interesting names. And then the example of oxygen here is an example that we will talk more about of a double bond. Oxygen has 6 valence electrons. It needs 8 in order to have a full outermost energy level. So it could, like in the previous example, make 2 bonds with 2 different atoms, 2 different hydrogen, or, and this is what happens in the oxygen gas that we breathe, what happens is it makes a double bond. And what is a double bond? Well, a double bond is what we see right here in the middle, where oxygen shares, one oxygen shares 2 electrons, the other oxygen shares 2 electrons. So they share 4 electrons, which is 2 bonds. And again, if I look at the outermost energy level of like this oxygen atom, right, I see, yes, there are 8 valence electrons. So again, comparing molecular and ionic. Just as a reminder, why do atoms bond? We know atoms bond to get that full outermost energy level. Usually that's 8 valence electrons, but if it's a smaller element, it may be fine with just 2. When you have a metal and a nonmetal, how do they get that full outermost energy level? Well, they bond ionically. That's an ionic bond. And we can see that's over here, where there's a transfer of electrons. The metal gives its electron to the nonmetal. And you have a negative ion and a positive ion, and the ionic compound sticks together because opposite charges attract. In a compound that's covalent, where you have 2 nonmetals, what goes on there is a sharing of electrons. One atom shares its valence electrons with another atom, which in turn shares its valence electrons with that first atom, and they share 2 or 4 or 6 electrons, depending if it's a single, double, or triple bond. And that's how those compounds are able to get that full outermost energy level. And the wording that we use to talk about these can be a little different from each other. If we talk about, an ionic compound, then all of those negative and positive ions come together in that crystal lattice that we talked about. And you can see it on the right side here with the example of salt, in that there may be in one crystal of salt millions and millions of NAs and millions of Cl positive and negative ions, Na positive, Cl negative ions that stay attracted to each other in this crystal lattice. So the chemical formula for that, we sometimes call it the formula unit, right? It's just the ratio of the positive to negative ions. Because we never want to say exactly how many negative and positive ions are in there, because every single in a shaker of salt, every single one of those crystals probably has a different number of positive and negative ions, but the ratio is always 1-to-1. In a molecule, so covalent between 2 nonmetals, you get distinct units that we call molecules. And we'll look at the definition of a molecule in a moment. But you can see how it's a little bit different. These molecules are not attached to each other. It's not a larger array as it is in anionic compounds. These are individual units where the nonmetals have come together, shared their electrons, and now they have a full outermost energy level. Their chemical formula is not the lowest ratio, it's the actual number of hydrogen and oxygen atoms in that molecule. So whereas in a salt, we say NaCl because the ratio is 1 sodium for every 1 chlorine. When we're talking about water, we're not talking about the ratio. We're saying a molecule of water will always have 2 hydrogen for every 1 oxygen. So then what is the exact definition of a covalent bond? Well, a covalent bond is when 2 nonmetals, and this is the big word here, they share electrons. They share electrons in order to get that full outermost energy level. And a molecule is a neutral group of atoms held together by covalent bonds. And I want to make sure that we use neutral group, because what this is reminding us of is those polyatomic ions that we learned about last chapter. Remember last chapter we learned about nitrate and hydroxide and acetate, those polyatomic ions. Well, if you think about hydroxide, right, what hydroxide is a 2 nonmetals, oxygen and hydrogen, where they do share a pair of electrons. So it sounds like we could call it a molecule, but because there is overall 1 more electron than there are number of protons, it overall has a negative charge. So we don't call that a molecule. It's not a molecule of hydroxide, it's an ion of hydroxide because it does have that charge. So this would not be considered a molecule. This would be considered a polyatomic ion. A molecule would be something very similar, but where there are the same number of protons as electrons.